Assalamualaikum. I will explain about the introduction for our project. Reverse and natural drainage channels are essential for managing runoff, reducing flood risk, and maintaining ecological balance. In Malaysia, frequent flash floods are caused by inadequate channel capacity, sedimentation, and vegetation growth. Hecras software is used to analyze and simulate river flow, which is unsteady, helping evaluate existing channel conditions and proposed improvement. This study uses Hecras to assess Sungai Sembrong, Johor, focusing on hydraulic performance and channel modification, which is widening and deepening, to reduce the flooding. It also includes cost estimation based on excavation requirements using standard engineering rates. For the problem statement, Sungai Sembrong experienced periodic overflow during heavy rain, causing localized flooding and erosion. Problems include narrow channel width, steep slopes, sediment buildup, and vegetation encroachment. Current channel section cannot convey design discharge during peak event, resulting in overbank flow. A detailed hydraulic analysis using Hecras is needed to identify critical sections, suggest modification, and estimate costs while maintaining environmental stability. There are 4 objectives for this project, which is number 1, to analyze existing hydraulic conditions of Sungai Sembrong using Hecras. Number 2, to propose and evaluate channel modification, which is widening and deepening, to improve flow capacity. Number 3, to estimate modification cost based on excavation volumes and construction rates. And lastly, is to compare the channel performance before and after the modification. Thank you.
Next, for the literature review, I will be explaining more about the natural drainage and the studies of this group assignment. Natural drainage systems are made of geomorphic features like natural channels, floodplains, wetlands, and catchments that help convey runoff, store water, and reduce flood and erosion risk in a more natural way compared to the engineered drains. In rural areas, natural channels play an important role in carrying flow, but their effectiveness depends on factors like shape, roughness, vegetation, sediment movement, and how well they connect to the floodplain. When a channel is too small or disconnected, overbank flow can happen, which may lead to flooding. According to the Harry II Barnes Jr., the roughness coefficient or Manning's, the value of n, is still something that requires both experience and judgment to estimate correctly. For this assignment, the chosen n value of 0.035 for a grass-lined natural channel fits well, since vegetation and surface irregularities strongly affect how water flows. Hydraulic roughness refers to the resistance caused by channel surfaces, vegetation, and bad materials. Archimedes 2000 also noted that the N values depend on a plant type, density, bed material, and flow condition. Studies show that higher vegetation density and submersion can greatly increase roughness and reduce flow velocity. The efficiency of drainage channel can be judged by its ability to convey flow without overtopping, maintaining stability, and stay connected to its floodplain. However, problems like sediment build-up or dense vegetation can reduce conveyance. Next will be continued about this literature review. To manage this, the reduce of conveyance, the natural channel design (NCD) approach focuses on restoring channels that mimic natural stable forms. Research also shows that branching drainage systems can help reduce overbank flow by providing more conveyance paths and storage areas. In Hecras modeling, Choosing the right N value, such as 0.035, is important for accurate flow simulation. If overbank flow occurs, modifications like widening the bottom width, flattening side slopes, or improving flat plane connection can be considered to enhance flow capacity and stability. Overall, natural channels can effectively manage flow when designed and maintained properly, balancing both hydraulic performance and ecological sustainability.
So, for methodology, there are 5 important steps that we need to know. We're going to go through one by one. Step number 1 is starting new project. So, in the first day of our class, we learned that we need to click File and then click New Project, and then you need to save whatever name that you want to put. After that, we need to entering geometric data. So every group have different data. This is our group data. And after we enter the data, we're going to get these two images. Step number 3, we're entering the flow data and the boundary condition. Number 4, we're performing the hydraulic calculation, which is after we put the data, we're going to use the calculation in this hydraulic calculation, and we're going to get the result. Last step is viewing and printing result. So we can click view. For example, we click cross section, and then there's the results going to show.
Okay, so I will continue to present about cross-section analysis that was obtained from the Hecras. Okay, first, the cross-section at channel 0 has a narrow bottom width, which limits discharge capacity during peak flow condition. At channel 100, the side slope are steep, increased erosion risk. The flow velocity may be high and could require stabilization measure. For channel 200, the invert elevation is relatively low, which helps with drainage but may cause backwater effect during high tide or storm event. At channel 400, the channel is moderately wide, however, vegetarian growth along the banks and may obstruct flow and reduce hydraulic efficiency. In channel 600, the section has a good slope profile, but its depth is insufficient for expected runoff volume, especially during the monsoon season. Okay, next, for the cross-section at channel 750, is prone to overflow due to a limited cross-section area, indicate that bank reinforcement may be necessary. At channel 850, the geometry is suitable for normal flow but lack capacity for stormwater surge. Therefore, widening or deepening should be considered. For channel 950, the channel has a flat slope, which may lead to sediment deposition and reduced velocity. At channel 1100, the section is structurally sound but may require desilting to maintain its design capacity. And finally, for the channel 1240, represent the final outlet which must be optimized for maximum discharge to prevent bottleneck or obstruction.
For this session, I will explain the channel modification process. There are two methods for this modification. The first one is widening and the second one is deepening the channel. At channel 0 and channel 100, the bottom width was widening to 10 meters and both the left and right side slope was set to 1:1. The invert elevation for channel 0 is 0.36 meters, while for channel 100 is 1.14 meters. Similarly, channel 200 and channel 400 were also widened to 10 meters with both side slopes of 1:1. The invert elevation for channel 200 is 1.63 meters and for channel 400 it is 2 meters. At channel 600, the bottom width was widened to 10 meters and the invert elevation was set at 2.05 meters. Meanwhile, channel 750 was widened to 20 meters with an invert elevation of 3 meters. The bottom width for channel 850 is 10 meters, while channel 950 has a bottom width of 20 meters. Both channels have side slope of 1:1. The invert elevation for channel 850 is 3.2 meters, and for channel 950 it is 3.4 meters. Lastly, channel 1100 and channel 1240 share the same bottom width of 20 meters and side slopes of 1:1. The invert elevation for channel 1100 is 4.29 meters, while for channel 1240 it is 4.4 meters. For the cost estimation related to the channel modification, we conducted research on the excavation cost. Based on the JKR standard, the cost of excavation is approximately Rm 30 per meter cube. From the calculation, the total cost for channel 1 is Rm 70,149 ringgit, while for channel 2 the cost is Rm 10,603. Based on this estimation, channel 1 has a higher cost compared to channel 2. This is likely because the existing river at channel 1 is shallower, causing water to flow poorly and resulting in blockages due to the accumulated debris. Therefore, more excavation work for required in channel 1 compared to channel 2.
Lastly, for our conclusion, the comprehensive analysis and subsequent modification of two channels reveal a direct correlation between the pre-existing geometric condition and the resources required for hydraulic improvement. Channel 1, characterized by its initial restrictive cross-section and limited discharge capacity, demanded the extensive widening and deepening. This led to a significantly higher excavation volume of 571.62 meter cube and a correspondingly greater cost of 7,149. Conversely, channel 2 possesses a more stable and wider inherent structure, requiring only minor adjustment to achieve the desired flow capacity, which result in a lower excavation volume of 353.43 meter cube and a cost of just 10,603. Ultimately, the project successfully enhanced the performance of both channels, with channel 1 showing a more dramatic improvement due to the substantial work undertaken, while channel 2 proved to be more cost-effective case, achieving its target capacity with minimal intervention.